Ever stop to think about what a bolt of lightning, the smartphone in your hand, and the entire power grid have in common? Well, it turns out they all play by the same secret set of rules, these invisible laws that dictate how energy works. And today, we're going to crack that code. I mean, think about it. It's this invisible force we use every single second of every day. But most of us don't really think about the fundamental principles that make it all possible. This force is, of course, electricity. But how does it really work? So, how are we going to figure this out? We're not cracking open a dusty old textbook. For this explainer, we're doing something a little different. We're going to decode the universal laws of electricity by breaking down questions from an actual engineering exam from Korea. It's a pretty cool way to see these principles in the wild. Okay, so here's our game plan. We'll start with the absolute basics of how electricity flows. Then we'll see how engineers use those rules to build circuits. After that, we'll explore the really deep, almost magical connection between electricity and magnetism. And finally, we'll see how it all gets harnessed to do some pretty amazing stuff. Let's dive in. First things first, before you can build anything, you've got to speak the language, right? So let's get into the fundamental concepts that tell electricity what to do. The very first concept we need to get our heads around is resistance. You can think of it as electrical friction. A material's properties, how long it is, how thick it is, all that stuff determines how much it pushes back against the current. The bottom line is simple. More resistance just means it's a tougher path for electricity to take. Now, the flip side of resistance is something called conductance. If resistance is like a tiny, narrow pipe that makes it hard for water to get through, conductance is like a massive, wide-open fire hose. They are perfect opposites. One is literally just the inverse of the other. So what does this look like in the real world? Well, an exam question on conductivity shows that silver is actually the best conductor there is. But right behind it is copper, which is a whole lot cheaper. And that, right there, is why copper is the undisputed king of wiring in our homes, in our cities, pretty much everywhere. Okay, so we've got the basic rules down. Now, how do we actually use them? That brings us to section 2, where we see how these building blocks get assembled into circuits, the grand design behind all of our electronics. A huge part of engineering is designing for when things go wrong, and a short circuit is a classic example of things going very wrong. It's basically when electricity finds a super easy shortcut it wasn't supposed to take, a path with almost zero resistance, which causes a massive and pretty dangerous surge of current. And check this out. One of the exam questions actually has us calculate this surge. So we combine the voltage of 5 batteries and then divide that by their combined internal resistance. And the result? 7.5 amps. Now, that is a huge flow of energy that can create a ton of heat, cause damage, and even start fires. And that's exactly why we have fuses and circuit breakers. Next up, let's talk about another key component, the capacitor. You can think of it as a tiny, really fast-acting battery. But here's the kicker. How you connect them is crucial. If you link them end-to-end in series, you actually reduce their total storage capacity. But if you link them side by side, in parallel, you get to add all their power together. And the difference is just staggering. Another exam question reveals that connecting 10 capacitors in parallel gives you, get this, 100 times more storage capacity than connecting those exact same 10 capacitors in series. 100 times! It's a perfect illustration of how circuit design isn't just about what parts you use, it's about how you use them. All right, now we're getting into one of the most beautiful concepts in all of physics. It turns out electricity doesn't operate alone. It's locked in this incredible cosmic dance with another invisible force, magnetism. To understand this dance, we need a new term. It sounds a little complicated, but the idea is actually simple. Magnetomotive force. Just think of it this way. If voltage is the pressure that pushes electricity along, then magnetomotive force is the pressure that creates a magnetic field. It's the magnetic version of voltage. So here's the first step of the dance. Whenever an electric current flows, especially through a coil of wire, it generates a magnetic field. This isn't just a neat party trick. It's the magic behind every single electric motor, from a tiny little fan to a massive high-speed train. You put electricity in, and you get magnetic motion out. And now for the return step. A changing magnetic field does the exact opposite. It creates a voltage, it induces an electrical current in a wire. This is how we generate almost all of our power on Earth. We spin huge magnets inside massive coils of wire at power plants, and electricity comes out. They are two sides of the same incredible coin. So this leads to a really fascinating question. If magnetism is created by electricity, then how do permanent magnets, like the ones on your fridge, stay magnetic without any power source? The answer lies in a property called hysteresis, which is basically just a fancy word for magnetic memory. The answer really boils down to two key properties. First, you have remanence. That's just how much magnetism a material can hold onto. And second, you have coercivity. That's how much force it takes to erase that magnetism. So to make a great permanent magnet, you need a material that has a lot of both. It has to hold a strong magnetic memory and stubbornly refuse to let it go. Okay, for our final section, let's bring it all home. How do we turn all of these abstract principles into real-world work, into heat, light, and things that honestly feel a little bit like practical magic? Let's start with something called Joule's law. One of the exam formulas points to a simple fact. Whenever a current flows through something that has resistance, it creates heat. Now, this isn't a bug, it's a feature. It's the whole reason your toaster works, your electric stove heats up, and your hairdryer blows hot air. We are deliberately using that electrical friction to create warmth. But not all power is created equal. The power that does the actual work, like turning a motor, is called effective power. Then you have this other thing called reactive power, which is kind of like ghost power. It gets stored and then returned by the circuit, but it doesn't actually do anything useful. Both of those together make up the apparent power, which is the total power being pulled from the system. And finally, for what I think is the most magical application of all, electrolysis. An exam problem asks what happens when you pass a current through a copper sulfate solution. Well, the electricity actually forces a chemical reaction to happen, pulling pure copper atoms right out of the liquid and depositing them as a solid. Over an hour, nearly 12 grams of metal literally appears out of thin air, well, out of the solution, thanks to the current. It is basically modern-day alchemy. So what have we really learned from cracking this engineering exam? We've seen that resistance and conductance are the push and pull of electricity. We learned that how you build a circuit is just as important as what it's built from. We saw that electricity and magnetism are locked in a constant dance, and that by understanding these laws, we can make them do just about anything. You know, when you think about it, from just a few simple rules, we built the entire modern world. The principles we uncovered today were the engine of the last 100 years of innovation. Which kind of makes you wonder, what new hidden laws are we just beginning to understand today that will completely reshape the century to come?